Good afternoon, everyone. It's a pleasure to see a lot of students here today. I think it's the right place to come to hear about possible career opportunities in the industry. You all seen Dr. Ramaswami's CV, so I won't talk much about that. I'll give you a very personal introduction since I know him for a very long time. I often say that I went to 3 universities, IIT Kanpur, Cornell, and Bell Labs. Bell Labs is where I met Dr. Ramaswamy. He was one of our senior researchers there, and I learned a lot from them. It was amazing how they were able to take abstruse concepts that we learned in school, in college and university books, and apply them to real problems. That was the wonder of Bell Labs. It was actually able to engage top scientists from around the world, literally from around the world, to build the telecom system which we have been using for several decades now. Quite remarkable. Dr. Ramaswamy, along with 2 or 3, his advisor, Professor Marcel Newts, he and 2 or 3 other researchers, Guy Latouche and Luc Antoni, were the ones who actually made queuing theory work. That means apart from having the simple MM1, MG1 queues, which all of us read in textbooks, and which you didn't find much use for, they actually gave us algorithms to be able to apply these techniques to real problems by extending those queuing models to more realistic settings, and thereby being more useful in applications that we often encounter in all sorts of systems, service systems, telecom systems, manufacturing systems, and so on and so forth. So that was the power that these 3 or 4 people, the school of algorithmic queuing theory, gave to us. And now most of it is available in software which you can download from the websites, and you can just apply it, like I did recently with one problem that I was encountering. So I guess that in a nutshell tells you about the impact that Professor Ramaswamy had on me and on queuing theory. He had another impact on me which probably is a bit more personal. I had grown up in North India experiencing the idlis and dosas of Kanpur and Agra, but when I went to his house the first time, I got some real South Indian food. So thanks very much for introducing me some good stuff. Ram, all yours.
Good afternoon, and thank you. I guess I should say Dr. Kumar. Anurag, okay, I'll take the liberty, all right? The dosa story, my wife is the guilty party, not me, okay? I want to make that very clear. I can't cook anything. I hope by now you have all read all these questions, all right? I'm not going to answer them one by one. This whole talk will become terribly boring. I will start looking more like a preacher than like a mathematician if I were to do that. So what I'm going to do is jump straight into some examples. As we discuss that, I'm sure you will see the answers to the questions yourself. In any case, at the very end, I will pull up one slide which at least gives the highlights, okay, of the things that I have learned by working on things of this type. The way this talk came about was, usually when I teach a course in queuing theory, which I occasionally do as an adjunct at a university or so, this is what I use in the first class to make sure that the students don't drop the course, okay? Because it can get pretty dry and boring otherwise. So somewhere up front convince them, yes, this is for real, we do use things and it is useful, all right? Some of you who are, if you find it too elementary, boring, please bear with me. Keep the context in mind in which it was generated, all right? Okay, I'll start with this slide, okay? Let's say one morning you wake up, have your coffee. This is the headline you see in your favorite newspaper. I put the Hindu, okay? Photoshop. The OR you will think about is this guy, right? You're not going to an operating room. You're not going to think about operations research, a bunch of mathematical equations, queuing theory. None of this is the kind of things, the imagery that that headline would have created, okay? The first example that I want to present to you is one where I was lucky, and I want to stress this very much, okay? It's not like every piece of work we do is of this type. You have to be in the right place at the right time. It happens. This particular piece of work happened to come my way, and what happened was one day our director walked into my office. You see, in research, the way the research area was set up in AT&T, some of us were left alone, okay? Nobody told us, this is your project, you should do this, we'll have the results by this day. That was the story in professional services. The way the research works is people are pretty much left alone, and if you look at my work, about 80% of my work is very theoretical. But there was some understanding that, yes, we are available to solve the company's problems, number one. Number two, on an ongoing basis, at least once in 2-3 years, over a 3-year window, they had the right to look at not only your theoretical contributions, but also were you pulling your weight in some way to help the people in the company. And that's what determined your race, determined even whether you continue to be there or not. All right, so one day my director came to me and said, look, I have a problem. I have a call from one of our divisions, and I'm flying over to Denver. Will you humor me by coming with me? Okay. Again, the culture is one not of ordering, saying thou shalt come, but saying this might be a waste of time for you. Would you please come with me? All right. And I was curious, so I said, okay, I'll go with you. All right. Luckily, as I said, there's a paper on this which was submitted for the Wagner Prize of Informs, bubbled up as a finalist. There's a very interesting story behind it. The prize itself was won by a paper from the Merrill Lynch Bank. And the purpose of the paper was to show how Merrill Lynch Bank could reduce its risk reserves by $3 billion. And the $3 billion is a big number, okay? Except Merrill Lynch Bank doesn't exist today. It went bankrupt in the 2008 crisis. Okay, so anyway, saving lives is less important than $3 billion. That's another lesson you learn in industry up front. This generated a whole bunch of US patents as well, which have subsequently been licensed and all that, and have generated significant revenue. That's at least what I hear from the unofficial sources, okay? The problem was this: AT&T had gone and acquired a lot of cable companies, and they wanted to integrate everything together, television, data, and telephony. So they were offering telephone service over cable lines. And we were in a situation where there were very large areas, including metropolitan cities, which did not get dial tone for like 3 or 4 hour stretches. And this was the pre-wireless time, okay? It was not like wireless telephony had become, today, many homes don't even have a landline. So in those days, if you don't have a dial tone, if somebody is having a heart attack, you're really in trouble, okay? So in that sense, it's a very serious problem. And subsequently, we went and did an analysis of, for one city, okay, like Denver, how many life-threatening emergency calls would be generated on a day during these 3 hours of not having a dial tone. That number turns out to be 90. So even if about 5% of the lives could be saved, you're talking about something big impact. But for the business, there are cases where telephone companies have settled for $150 million as punitive damages and all in the past. So this is also mega bucks, okay, at risk for the company. Now, people always ask me, why can't you do priorities, okay? To implement priorities, you have to first get the digits dialed by the customer, recognize it's a 911 emergency call. If they don't even get a dial tone, what do you know? Nothing, right? And what the cable guys had done was, we had an information lab with our own proprietary database, highly optimized with a language of its own called Symbol. It's totally internal to AT&T. So they said, since you have all these tools, we will give you the customer complaint data, the maintenance logs. We will also give you the network topology. Can you hash these together, find out what is being done incorrectly by our maintenance staff? Because right now we're spending a lot of money in sending people to their homes in trucks. They're wasting the time, finding nothing, and coming back. Can you help us? For me, my question was, could this be a congestion problem? Okay, because, and I'll show you why I had that doubt. See, over here is a switch, okay, a telephone company circuit switch. Here is the public switch telephone network. In the good old days, you as a customer, your phone hangs straight off that switch through a copper wire. You pick up your handset, immediately the switch knew that some circuit was cut. You got connected to a dial tone machine. You got your dial tone, which is a signal that, okay, go ahead, dial your digits, I'm ready to accept them, etc. But today, what we have done is we have put a lot of middlemen between the phone and the switch. In the cable case, you come on a street cable, then go onto a feeder cable, somewhere you get onto an optical network, to a head-end data terminal, and it is this guy who either directly connects to the switch, or in between there might also be an internet cloud and all that, we don't know. All right? And again, I want to stress for those of you who are in ECE and all that, we are talking about circuit switch telephony, not packet switched, okay? Packet switched is here, you have the DOCSIS protocol and all that, that's a different system. So one of the questions I asked him was, do your customers use these telephone lines for internet dial-up? And the answer was yes, of course. And I asked, why would you let them do that? Because that hogs the lines for a much longer period of time. And their answer was that these are sold by two different parts of the company. This costs $30 more per month. In fact, we are using this as a loss leader to sign up customers for the bundled service. And a lot of people don't opt for the packet system on top of it. So we have, okay, that's what they said. So I said, look, this is where the problem might be, because I had seen it earlier in my job in Bangalore with some ISPs. So what they did was they brought their traffic team immediately. See, one difficulty with problem with performance analysis is we are seen as the troublemakers, okay? If our job is done well, nobody sees it. But when there's a problem, you go there, you're seen as somebody who might be pointing a finger. So these people got very defensive. They said, one minute, okay? So again, it was, what I did was I had from them taken some data for 1 week. I did a quick and dirty data analysis of that, saw two interesting things. One is, most of the customer complaints were coming from between 7 p.m. and 11 p.m., which is the residential busy hour. That clearly tells me maintenance cannot be a problem. Maintenance is union labor, okay? They come in, punch in at 8 o'clock, punch out at 4 o'clock in the evening. So there's no maintenance guy mucking around between 7 and 11 p.m. The second is, the cable network is inherently a tree-structured network. You have a feeder cable from which the street cable comes, there are taps, same thing at the fiber level. So if somebody is mucking up upstream, you're going to see a lot of geographical pattern in the complaints that come, clustering and so on. Whereas the data did not show any of those patterns. Between the two, I was quite convinced that I was on the right track. All right? But the engineering guys, they got very upset. They said, we are following standard engineering procedures, and I got a fairly long lecture on, do you know, there was a guy called Erlang who in 1919 invented queuing theory, and those are the methods we follow. The second complaint got was only 5 to 8% of the calls are of internet type. How much damage can they do? And the third one, which is a killer, is we have taken field measurements galore, and we don't see blocking on the circuits. Okay, so you can't be right. So it became quite a challenge. So one of the things I did was got their billing data, and what I'm showing you here is a histogram of the distribution of the holding times for the calls, how long the call lasts on a logarithmic scale. I don't know how many of you can see this. Do you see this green curve here? That is our familiar exponential distribution, okay, which is the one that is used so often in queuing theory as a simple model. The exponential looks like this because, remember, I made a log transformation, so there is an additional term that comes up, in case you're wondering why it doesn't look like an exponential distribution, okay? So this, anyway, doesn't look anything like an exponential, that is one. Secondly, this distribution has fairly very long tails, as you can see. This is 10 to the power 4. Yeah, 10 to the power 4. So there are calls lasting as long as a, what is it, 10,000 seconds, okay? Kids downloading videos and things like that, all right? So one of the things I did was I work a lot with a class of distributions called phase-type distributions, which are built on Markov models. And I fitted one of those distributions using an EM algorithm to the data. And this curve which you're seeing hugging the histogram is actually the fitted distribution. I don't like to run away just showing graphs because you can play games, but here is a table, okay? Actually, the observed percentiles and the fitted percentiles. You can see that there is an excellent match up to about the 99th percentile in between the data and the fitted model. All right? Now comes the interesting problem. There is something called an insensitivity theorem in queuing theory, which says that if calls come as a Poisson process, the blocking probability depends only on the average length of the holding time and not on the actual distribution. Okay, so when these people were talking to me about the work of Erlang, they were referring to not only the Erlang's blocking formula, but also the insensitivity theorem, saying what, so what, you know, all right? So one of the first things I did was, for a phase-type distribution, it's very easy to calculate the residual distribution. Let me explain, you know, if you're not in probability. Imagine you have something like a bus that comes every x interval of time, where x is random, okay? That's what you would call a renewal process. So the distribution is the same. The values may not be the same, but as a distribution, it is the same. Now, if you fix a time t, from there you look at the time to the next bus arrival. So you're not talking about an entire interval, but a partial interval. That's what we mean by the residual distribution. It's fairly easy to calculate for the phase-type distribution. I did that, and lo and behold, this is what you have. The whole distribution shifts to the right enormously. For our original data, the median was 48 seconds, okay? So 50% of the calls, including data calls, lasted only 48 seconds. But look at the residual median. It is 703 seconds. Same thing with the mean. All right, why am I looking at the residual? Okay, for that, I have a very simple way of interpreting this. The observed, the original distribution which I showed you in the previous slide came from billing records. It's like a post-mortem, okay? Customers have come, used the system, they've all gone, and I'm looking at the distribution of the total time they were present, and that's what I showed you. Here, think of an experimenter who does something entirely different. He comes at a random time t, measures the time from that point until the call will hang up, and create a distribution for the remaining time, and what you find is this guy. All right? So what's going on here, right? This is like, see, we have something called waiting time paradox, which people are introduced to even in a first course in stochastic processes. If you have buses which come on an average, let's say 1 hour in between randomly, people will still complain. Why is it that the bus I am waiting for is always late? Okay, Feller's volume 1, I think, already has that as the question. The answer to that question is the following. When you come at a time t, you are looking for an interval that covers that particular t. So a longer interval is more likely to cover that point than a shorter interval. So your sampling is inherently biased. It's a biased sampling, biasing towards longer values. Okay? And that's the explanation for that, why you feel like your bus always takes longer. Now, in this story, what really happens is only 5 to 8% of the customers are of the internet type, but these are big fish, okay? So if you come at a random time and look at the system and see how it is configured, how many are voice calls, how many are internet calls, you're going to see a much larger fraction of internet calls because they tend to get stuck. All right? So this tells me 2 things immediately. One is this system will be prone to congestion because of this biasing. Not only that, when congestion happens, that congestion is going to last a long time because many of the people sitting there are these big customers. So assume you had engineered the system based on averages and your calculation told you, I can load this system to 80% capacity, all right? But when the system is congested, let's assume that 30 of those lines are taken by internet customers. You're not, for that interval of time, which is like about, what is this, about 11 minutes or so on as a median, okay? You are running the system only with 70 circuits because these 30 guys, they are very long holding time customers. They're going to be sitting there hogging your system. So congestion will not only happen, when it happens, it's going to be persistent, last for a long time. All right? So the bottom line, so from the dial tone perspective, in US, for circuit switching, the dial tone delays are supposed to be under 2 seconds with probability 0.995 or so. Because people are so accustomed to picking up the phone and start dialing immediately. All right? Now, there's nothing wrong with the theorem. The insensitivity theorem says that the blocking probability over an infinite horizon, okay? If you were to look at an infinite horizon of time and look at what fraction of customers who are coming in will find all the circuits busy, that fraction is totally impervious to the shape of the distribution, depends only on the average. But are you going to wait for an infinite amount of time to get your dial tone? You're talking few seconds, right, of patience. And in those few seconds, there are going to be a lot of customers who are not only not going to get dial tone, the system is going to be so bad that it's very likely that congestion will persist for them. All right? So that knocked off one of their objections, which was we are following standard engineering procedures, okay? The standard engineering procedures were built for a different environment. The mathematics was on What happens in the system over an infinite horizon of time? We got away with it, but here we cannot. All right? And why did we get away with it? If all your intervals are short, the system in some sense is self-correcting. As the system gets built up more, the departure rate is also larger, right? But here, if there is a whole bunch of people who are going to sit there, your arrival rate is the same, your number of circuits has gone down, and the departure rate is actually getting lower. All right? So it is this business of applying a result which applies for very long time intervals to a problem that is inherently a short time interval that caused the problem. So that was easy. By the way, one of the things I tend to do in the work, especially in serious applications, is to try to validate the models against data. Very rarely this is done in queuing work, okay? That's one of my complaints. So what we did was we actually went and took 11,000 samples by sampling the system, come at an arbitrary time and measure how much longer calls last from that point we came in. This is the model that was fitted, that residual distribution, the histogram is the actual data. Yes, there is some discrepancy at the tail. With 11,000 observations, you don't expect to estimate the tail in the third decimal and all very accurately. So statistical fluctuations, number one. Secondly, I got lazy, okay? I had used what they call a uniformization procedure, and I didn't do any optimal truncation or something of the infinite series. I just, and you know, to me, I'm pretty happy with this, that the model really jives well with the data, okay? So this is all that I told you, all right? That is, insensitivity relates only to an infinite time horizon, whereas here you have persistent congestion over shorter periods of time. By the way, the insensitivity theorem is still valuable. So you have a schizophrenic system which over short intervals will totally misbehave crazily. If that's the case, for it to give you the same average rate over a very long interval of time, in between there should be very gold-plated intervals, right, where the service is just super. All right? So what you have is a really schizophrenic system. Either it behaves as an extremely over-engineered system or as an extremely under-engineered system. The persistence, what it tells you is, this is also an ideal system to control. Because, see, you don't want a control that you have to invoke many, many times. That would be terrible. So if you put in any control, this gives you the hope that once the system is controlled in some way, it's going to behave well for a very long period of time. Okay, so it's a very ideal situation for somebody like a queuing theorist who want to build a congestion control algorithm. All right? So taken care of that. Here comes the biggie, okay? Remember, they said we have taken measurements galore and we don't see any blocking. That question still needs to be answered. And you know, I don't blame them. You see, I as a mathematician, as a researcher, go there, I give my answer, walk away. But they are the ones who have the responsibility, right, ultimately. So if they are very defensive and not accepting my recommendations without asking a million questions, putting me through the fire, that should be absolutely acceptable, all right? These are the big differences in industry, all right? The one who gives the advice is not the one who holds the responsibility, and we need to respect that fact as people who go there as specialists. We can't take a very arrogant attitude saying, I know, and what do you know? You know, that doesn't work, all right? Okay. See, there is again a theorem, okay, in queuing theory which says that large server groups are more efficient than smaller server groups. This is the logic behind, for example, if you go to a bank in the US, and slowly it's coming here too, if you have a bank of tellers, usually you have one line which feeds that entire bank, and whoever is the head of the line goes to the free teller. Finally, after so many years of complaining, I see that the immigration here has adopted that policy. Earlier, you used to have separate lines for each counter, all right? In fact, the entire call center business is built on this fact. And it's built on a result which was invented by two of my colleagues, something called the Halfin-Witt theorem, using heavy traffic theory, which says that if you use very large server groups, you can achieve low delays and at the same time very high utilization, both at the same time. Typically in queuing systems, as utilization goes up, your delay gets worse, right? And very often the trade-off is very difficult. But with very large server system, that theorem shows that you can achieve both. An example of that is the following, all right? See, suppose I have a server group with 24 servers. In this case, 24 circuits. I put 24 because the standard T1 line has 24 circuits, and that's what is in a street cable that comes on. If you're shooting for a 1% blocking, that is 1% of the customers in the long run will find all these 24 lines taken, you can load the system only up to 59% of its capacity. At this point, you would reach 1% blocking. Suppose instead of 24 servers, you had a larger circuit group with 116. 116 I use for a specific reason, okay? Because I'll show you in the actual system, these are the numbers that I used. With 116, you can load the system for the same blocking probability to 82.5%. You can do the queuing computations, verify these numbers. This is what you mean by saying larger server systems are more efficient. You can load it up a lot more to get the same blocking result. But the real world has no free lunch, all right? Something has to give. And what gives is, because you're loading it more, you're taking a bigger risk. If you think in terms of these excursions of this stochastic process, this process has a much bigger risk of building up. And the way you see that is if you look at, let's say, the 2 mu plus 2 sigma limit on the number of circuits occupied for these two systems, for the 24 circuit system, this mu plus 2 sigma is only 21.8, round it up, 22 circuits, okay? You still have 2 spare circuits, even with that fluctuation. Whereas on the 116 circuit, when you load it to 82.5%, the mu plus 2 sigma number, round it up to 116, you're exhausted. All right? So this is a myth, okay? In some way, it's a myth. The fact that larger service systems are more efficient. You're taking a bigger risk. Now, if all your customers are nice, then the self-correcting mechanism helps you. As the queue builds up, more people are also leaving, okay? But if a sizable number of them are getting stuck, you are in big trouble. You'll be exhausting the circuits. So that explains the dynamics of the system. And in terms of the story, the company was in 2 different parts of the business. Somewhere here was the dividing line, okay, after the head-end terminal. The cable guys had visibility only to this part of the network. This part belonged to AT&T long lines. All the problems were happening here, where there were 116 circuits. So in other words, you were multiplexing a lot more, using much bigger service systems here, and that was not at all visible to our cable guys, who were taking measurements only on this side with 24 circuits. Okay, so in a sense, we had to tell them, guys, you haven't done anything wrong. We are not blaming you. We queuing theorists have not recognized that this kind of a problem could happen in this environment. We have always believed in all these heavy traffic results and all the limit theorems. This is a different ball game. In fact, when I did all this, the results were delayed by 2 months just because Ward Witt, who is my colleague and one of the most highly respected people, he had difficulty believing it. He had to build a simulation himself, run it, Then one day finally he came and told me, Ram, you're right. Okay? So even to a fellow mathematician, convincing that the mathematics is right sometimes takes effort. So who are we to complain about a field engineer who bears a lot of responsibility, right? We need to have much greater respect for that. So put all this, okay, I think I talked about all these things, so I'm going to skip all this. By the way, who cares for circuit switching now, right? It's all old technology, but it's still not true. If you go to Denver, still we have a lot of customers who are circuit switched. Right? What we had to do here was to, let me see, slide. Okay, I'll talk my way through. It looks like I accidentally erased that slide. The paper has all the descriptions. See, in most of these problems, okay, once you know what the problem is, the starting point of the solution is common sense. Where mathematics and models come in is in refining and quantifying your common sense. Now, you know what the problem is. Too many internet customers are in the system and they hog the lines, right? So what is the solution? If you ask anybody, the solution is do not let in too many internet customers at the same time, right? So if you can keep track of how many circuits are already taken by internet lines, put a threshold and say, beyond this point, I'm not going to admit any more dial-up customers. Or if you're clever to say, okay, I'm going to bump the oldest guy, the one who's been hogging it for longest, replace him with the arrival. You can have many different kinds of things you can do. The thing is, whatever control you put in has to work on a firmware in real time. So that's where the patterns come, okay? Just to give you an idea. Where do you get 5 or 6 patterns on that? The 5 or 6 patterns come because you can put in a control, but this control, you need to take into account all factors, okay? Like for example, most internet dial-up, it's an automatic redial, unlike a human who dials. So if you don't put in some additional controls, okay, you're going to pick the next call, right, and bump somebody, let's say. How do you make sure the next call is not another internet call again? If you don't have any control, if the internet callers are auto-dialing, it's very likely that you replace one bad guy by another bad guy, right? So that's one area where a pattern comes. Another one is usually we implement a last in first out system for dial tone queues. Now this completely messes up with that. So you have, and I don't want to get into why and all that, okay, that'll take us far afield. The basic idea is if you don't have that, if you use a first in first out, you can end up in situations where your throughput is high, where your good put is bad, in the sense you're spending a lot of work on calls you cannot complete. Those kind of things can happen. So when you take all the side effects into account, you get all these different patterns and different combinations, so on. We had to do 2 things, okay? One was, remember, the company won't let anything happen until the patent is filed. The patents themselves, it's not like we build the equipment. Some other vendor builds it. They have their cycle of new releases and so on. We cannot be waiting for 1 year for the solution to be implemented, even if it's good. So we had to put in some band-aid. Okay, the band-aids we put in was essentially to say, rearrange your customer groups on these head-end terminals differently, so that you get a better mix of business and residential customers, because their busy hours don't overlap. Residential customers have their busy hours in the evening. The business customers have them during the day. So with a proper mix, again, we have to do quite a bit of computations to tell them what is the right mix and so on. And you do this, except it was a bad solution for the following reason. Somebody has to physically go, pull out wires, rearrange them. That means downtime for customers. Okay, that's why the long-term solution is still good and is the way to go. Okay. Now, I was about to say, who cares for dial-up internet anymore, right? But one nice thing with mathematics is you solve one mathematics problem, you have a whole slew of them which are isomorphic to it. Think about all these following problems. Call center engineering, okay? What is your experience with call centers? Like let's say an airline ticket or an airline inquiry center, whatever. Most of the time, you go through with no problems. And there are times when you are stuck there forever, right? The half-in-width theorem is based on an exponential holding time distribution and asymptotics and an infinite horizon, blah, 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 okay? And you see the effect of that in real-world call centers. They are schizophrenic. There are times when you go through just like that. There are times you're there forever. So we've used the same ideas in some AT&T call centers, okay, to improve that kind of behavior. So that's one example. The second example, see, if you look at the dynamic and real time, by the way, this is an open problem, okay? Nobody has really worked on it in a serious way, solved it. If you look at all the literature on dynamic real-time controls of routing traffic in networks, typically people look at a 3-node network. If a direct path is not available, you send the customer on an alternate path. You don't want to use the alternate path too much because now you are occupying 2 circuits instead of 1, right? Now, if you look at all the existing algorithms, the work of people like Debasis, Mitra, and a whole bunch of others, which built this theory, it's all built on exponential holding times. It would really be fun to redo those calculations with some heavy-tailed holding times, at least a mixture, and see how well those results will stand up. And I'm willing to bet a reasonable amount that they are not going to work well at all, okay, based on what I see here. Same thing with the internet and high-speed communications. See, when you use things like labels, switched routing, and all, a lot of the packets follow the same path, okay? For periods of time, especially if you have very large payloads, interleaved with small payloads, the systems can exhibit behaviors of the same type. On top of it, you have one more complexity in broadband networks, which is you have input lines which are high-speed lines and also low-speed lines. So again, this is a fairly open set of issues to look at. Okay, what are the real challenges here? This one is very interesting. I don't know whether any work is done or not. I have not followed up. Okay, Professor Kobayashi at Princeton wanted me to make a presentation on this particular piece of work because he heard this in the Wagner Prize competition when I had given the talk. And the reason why he wanted me to talk about it was the following. See, when you want to do a denial of service attack of an internet site, the usual thing we think of is hitting them with a lot of packets, right? But apparently, the work of his students had shown that one effective way of hurting an intranet is to send very large payloads, interleave them with small payloads. That can completely mess up the engineering of it. So he wanted his students to be sensitized to the fact that when they look at the kind of controls they were putting in to prevent the systems from suffering from these kinds of attacks, they were covering all the bases. Okay? I don't know how much work was done on that, but if anybody is interested, I would say chase this baby. Okay? I will try to go a little faster with the next example. So where do problems come? Okay, in this case, the problem came because some director thought, here is this queuing theorist who is taking my money, doing nothing. Can I make him busy for a few hours? Okay, and that's how that work came. This one, see, again, the papers are here, and I will leave a copy of the slides after adding that one slide on the congestion controls we developed and all. Okay, and so the references are right there. See, should the communications people are familiar with the SS7 network. Basically, you have the voice network. On top of it, there's a logical network, which is a signaling network, which is used by switches to talk to each other. So when you send a call from here to, let's say, Los Angeles, it has to go through many different switches. So each switch at the call set of time has to say, I'm sending you a call destined to so-and-so on this particular trunk. And similar messages have to happen during call teardown. With advanced intelligent network capabilities, such messages go even during calls, like I'm adding an extra caller, things like that. Okay? So this is like the nerve center of the network, and typically every switch is connected to 2 signal transfer points, so that if one link fails, still they have another link, another signaling point through which they can exchange these signaling messages. So one day I was in the cafeteria, and a lot of the people were complaining, and the complaint was, in our vice presidential area, there were 3 entire departments running around all over the country, and were doing this for 2 months, because in many parts of the network, these links were chattering like 150 times a day. So links will go down, come back up, and this happens like 100, 150 times a day. All right? And they were going out, checking all kinds of cross connects and whatever else that is there on the network to see, is there any common pattern that is there? Is some manufacturer or vendor, is there a problem that generates too many errors or something? What is going on? And they were not finding any discernible pattern, anything. And they were really getting too tired, okay? They were saying, what is the point, okay? We are now asked to go back to the same places where we know we have already checked all this. And there's an interesting story, because I think it was 92 or something, okay? I had come back from an international teletraffic congress in Denmark, and my colleague, Len Forris, who is another traffic manager, he was also there in the same meeting. The moment we walk into the office, our assistant vice president is standing there yelling at us, how can both of you go at the same time and be so damn irresponsible? All hell is breaking loose. What happened was, one of the manufacturers of the STPs had designed a bad overload control. With the net result, it went down. It created a contagion. A whole series of STPs went down. And the US Congress did not have telephones for 7 hours at a stretch. It hit every newspaper headline. It was the story of the year. All right? So our 2 departments, and to a very large extent mine, was put in charge of cleaning up all the congestion-related issues related to the signaling network. And our AVP had to give every week a report to the Congressional Committee on what we had done, when we can say it's all clear. Okay, so that work had forced us to learn a lot of things about the SS7 protocols and all that, which came out to be very useful. So I asked these guys, is it possible that this is a protocol problem and this is not a hardware problem? I mean, if you guys have spent 2 months, 3 departments, running around looking at so many cross connects, so many STPs, so many circuits, there has to be something else. So one of my colleagues and I said, let's look at the error monitoring algorithms on these signaling links. Okay, I told you there are 2 signaling links, right? At that time, CCITT, okay, the standards, the international standards, had standardized an error monitoring algorithm. So what it will do is, it will keep looking at the signaling messages that are coming, will do a CRC check, and will keep counters on how many messages are coming without error and how many are error. Okay? And they have what the name is the leaky bucket algorithm, although in reality it should have been called an overflow bucket algorithm. The idea is the following, and I know again I don't want to get into the details. Roughly what it says is, if you get a set of D packets in a row that is good, reward yourself, so by 1. But every time a packet is in error, punish yourself, increase that counter by 1. Okay? All right, so every D packets, you reward yourself by 1, D good packets, but for every bad packet, you punish yourself by 1. And you keep count on this counter. If that counter hits a threshold, so that is your bucket filling up. If the bucket fills up to that threshold, then you say, oh, this link is doing badly, and shut it off. That is the leaky bucket algorithm idea. It protects you against 2 things, as you can see from the design. If you have dribbling errors that are coming, and if they are at a rate bigger than 1 over D, it will catch it. Because this threshold will slowly creep up. Right? Whereas on the other hand, over here, if you get a burst of errors, this fellow will make the bucket go up and it will shut off the link. So it protects against random errors as well as bursty errors. So very nice algorithm. But then in real life, a lot of the problems are transient. Okay? Somebody can be riding a lawnmower or something, create an electric or a thunderstorm. You can have an electrical disturbance which creates a problem. So if the link goes down, they report to a repair center. It takes a day at least for the repair center to act, to go and look at the link. And they go there, everything is fine. It has reset itself beautifully, all right? So what they do is they run a second algorithm. So when this algorithm shuts the link off, the international standards say, create a test packet and run another leaky bucket algorithm. And if it doesn't shut off the link by a certain amount of time, then do not resurrect the link which was turned off. All right, so you have one guy who detects errors, will shut it down if the error rate is too high. Another algorithm takes over. It keeps testing that same link. And if that algorithm doesn't again shut off the link, you bring it back up for service and let the signaling packets go through. Now, what is the price? Anytime you shut off one link, then there are signaling packets that are stuck there in that link. All those packets have to be moved to the other link. So a higher level protocol has to kick in. That introduces delays. The net result will be a lot of calls can be dropped. If it is an advanced intelligent network, some of the mid-call controls fail, and customers see the effect of that. And if the links start doing it 150 times a day, you can see why people in telephone companies were going crazy and were willing to let 2 entire departments run around the whole country to fix it. All right? Now, for me, this was a very ideal situation to use stochastic process models. Okay? For example, you can build a simple model where packets are of the same length. There's a probability P that they are either errored or not errored. And then you're looking at a hitting time problem. Okay? So you can, for both these algorithms, you can do that, do the computations. And here is, I mean, the paper has many different pictures for many, many scenarios. Okay? So I'll just give you an idea. In the case of the first algorithm, here are the error rates. Okay? You can barely read it. It goes from 10 to the minus 5 to 10 to the minus 4. All right? The reason I've chosen this interval is copper. For copper links, this is typically the error rates in which they operate. This guy, the first algorithm, as the error rate goes up, it should catch it, shut down. And what this curve gives is the probability that it will shut it down within, this curve gives you within a period of 1 minute, this within a period of 5 minutes. Okay? So we have different curves. The other set of curves are the probability of the second thing bringing it back up. 1 minute, 5 minutes, so on. What you see is this big overlap. Okay, there is a very big interval of error rates where both these algorithms operate with probability 1 or near probability 1. So one algorithm will pull it down saying the link is bad. The other guy will put it back saying, no, there's nothing wrong with it, and put it back, and this game will go on. All right? So we did this work, went to the protocol people, told them, look, I think we've found what your issue is. You have these two algorithms which are working against each other, and this is what is happening. So the answer that's given is, oh, but you've done this with random errors. In real life, errors don't happen random. We have bursty error scenarios, okay? So we come back, model, intuitively you know that bursty errors will make the story worse, okay? Think about it, you will convince yourself, all right? But these are not mathematicians or modelers, so we did all the math, did all the computations, went back, showed them the curves. Still, they're not willing to accept, okay? They say, but this is all mathematics, this is not real life. So one of the fellow department people, they really bought into this, okay? They thought we had hit it on the nail. Luckily, right in our complex, we had an STP, we had a switch. So they actually went and took measurements, did this game, and they showed that, yes, the math is right. The computations do check. Then the protocol guys again say, yeah, but this is all in the lab. This is not in the field. Finally, the way they resolved the problem was to put in an additional protocol saying that if the link chatters more than n times, take it off. Don't keep running both these algorithms. Not that it's going to solve the problem, all right? The reason I'm bringing this example is the following. I was very young. I was impetuous, stupid, whatever you want to call it, all right? Never understood the actual reason why these people were pushing us around saying this is only random errors, this is only a mathematical model, this is only a lab experiment. The unfortunate thing was the guys who were responsible for making the changes were the very same people who had designed these two algorithms and had proposed it to CCITT and ANSI. ANSI is the American standard. Now to go back to your bosses and say we screwed up 5 years back on something important like this, they couldn't come to accept, okay? All right? And we never understood this. We were like hitting our head against a brick wall again and again, as though mathematics and all the mathematical arguments and the lab experiments, everything will convince them. It did not. That's the bad news. The good news was, a year later when they had to build error monitoring for fiber networks for broadband, they came to us and said, will you guys design it for us? Because I think you guys are on the right track. So the current ITU standards are really based on our work, all right? And there what we did was we really modeled this problem along the ideas of statistical testing. You have a type 1 and type 2 error here, okay? The link may be good. You may wrongly take it out. That's one type of error. Or the link is bad and you don't take it. So you do the typical type of thing, you hold one error at a level and try to minimize the other error probability and design your link. And that is the idea we followed. There's quite a bit of mathematics and number crunching to do. It worked out very finely, okay? So that's the second example I want to give. I think we are running out of time. I'm going to skip the next one or... See, the next one is an example which doesn't have anything very dramatic on this, but it's interesting for the following reason. See, suddenly somebody in our cellular network people, they decided that our networks are getting overloaded, and then now today every Starbucks, everything has a Wi-Fi. So can I offload some of my cellular traffic onto Wi-Fi? So they wanted us to characterize the Wi-Fi traffic and tell them how many of the Wi-Fi channels on their, how many of the ports will be busy at a given time. And they said, don't worry about queuing and all, assume that these are infinite server queues for all your consideration because they are extremely over-engineered. Go ahead, do that. We went collected a lot of data and we found several things, and I'll run this through very quickly, okay? we found that there's not a single model really. Even their coffee shops are of different sizes. You can see this is the time of day here, starting from 3:12 a.m. going back to 12 a.m. In 15-minute time slots, we are showing the average number of ports busy on the Wi-Fi box. And we have classified into 4 different groups the various Starbucks. A Starbucks sitting in New York City right in front of the Penn Station terminal will be something like this, okay? But if you are in an area which is far away, like in the 110th Street, probably this is the kind of behavior we're going to see. So there's no one single answer. These are 2 different weekdays we are showing, okay? And you get a kind of a pattern, all right? At about 8:30 or so, people are coming to work, they're stopping to pick up coffee. They sit there, maybe quickly look at their email or send a message, whatever. You see things shooting up. Then around noon, the same thing, people are leaving work. Whereas in weekends, you don't see any of those patterns. And this work, what I did was, so how do you build this time dependence in your models? So we took these 15 minutes data, did a clustering analysis, found that using about 8, it kind of naturally broke up into 8 clusters in terms of mean clustering algorithm. So mean arrival rates, there were 8 distinct rates. And when we looked at the way clusters were formed, it was beautiful, okay? The 32 is like about, if you're talking 15 minutes, it's 8 o'clock, right? So 8 to 8:15. You can see there's an evening hour here. Sorry, this one, 8:30, around there. You have a peak. Here's another peak. So it did correctly identify where the peaks were happening and all that. So we said, okay, we will model it as a time-dependent Poisson process where the parameter, the arrival rate, depends on specific cluster, and within the cluster, that particular number of the slot it is in. Okay, so you have a lambda I comma j. That's kind of a model we used. And for the time-dependent Poisson, I have the model mean compared to the observed mean. Okay, and we did a lot of queuing analysis. One of the things in that paper is I have a new way of solving time-dependent Poisson infinite server queues. I basically create an integral equation and solve directly using that, okay, which is much more direct, elegant, and all than what you see in the literature, okay? But that's the side story. But here's another example, for instance, where we really took the data, formed the, you see here are the 2 confidence intervals, the 2.5% and 9.5% confidence intervals, generated with the time-dependent probability computations for these infinite server queues. And if you look at this, these little lines, okay, this light green, those are actually the sample paths. And I actually subjected myself to a much greater discipline like what a good statistician would do. We used the first 6 weeks of data to build the model and the next 3 weeks of data to do this analysis. Okay, so I'm not testing the model against the data which generated the model. Okay, the reason I'm presenting this example is a lot of times I see queuing papers where you have a model, you simulate the model and tell me the numbers agree. So what? You did the computations correctly. It doesn't tell me anything. Many times you don't have any real system measurements shown at all. Or when system measurements are shown, people compare like a mean or something, okay? That doesn't still convince me that your model is validated and good. All right? I think we have enough computational power sitting right on our desktop today. There's no excuse not to do these things unless you're working with a very large network or an extremely complicated protocol or whatever. Okay, so we did that, developed the guidelines. Again, there's a paper in one of the Infocom conferences on this, okay, and again, there are, see, the reason I'm putting this slide is because, you know, there's a general perception that applied work, this is not challenging. No, that's not true. I draw a lot of my theoretical problems from the applied work I do. All right? Now, all the queuing algorithms here are static. Life is not the same, okay? The Starbucks, which is not busy today, if the next coffee shop closes, it may change its profile right away, right there. All right? So you need to really upgrade your models periodically. If I were to take that paper, read it, you will see. Suppose I had to do everything, not with static data, but streaming data, including fitting this Poisson model and upgrading my Poisson model every week, but with streaming data. How would you develop efficient algorithms? It's quite a challenging problem, okay? Nobody has solved it. If you're looking for a PhD thesis or something, it's a very nice problem, because then you can automate it into a system, all right? You don't need, once you put it in, the system is automatically generating new models, working with them. Same thing, how do you extend this from Poisson to more complicated models, which have greater dependencies over time periods, so on. Right? So each one of these examples, although they came from specific problems, they give rise to a lot of interesting research problems, even of a theoretical type. All right? So I think working in an applied area like queuing, if you're really totally disconnected from applications, my feeling is that we're missing out a lot. Right? One way, the question is, if you're sitting in an institute or a university, how do you do that? For heaven's sake, read papers that discuss real applications. Okay, because there are a lot of things there, okay, that you will see, and many times you will see that things are done badly. That itself might give you enormous opportunities to do worthwhile research. Okay, so I will conclude with this slide. Okay, I asked what is the trade-off. The trade-off for me on the positive side has been continuous learning. Okay, I'm a mathematician. The first 2 years in Bell Labs, I was totally lost. I was told, write some papers from your thesis. I didn't know anything about any of even the jargon, okay, or the acronyms. We didn't know. All right, and it's an environment, and the technology is changing so fast. It's an environment where you're challenged to learn continuously, and that's an excitement. You keep yourself young, okay? If you're learning new things, you never get old. As I said, you get a lot of new problems. And, seeing our research come alive, doing something worthwhile, being implemented in a real system, to me, it is at least as satisfying as seeing a paper in print in Journal of Applied Probability or Advances in Applied Probability. In sense of being useful, okay? You see, in the very old days, if you look at Britain, the guys who did research, they were the nobility, who were rich. They had their money to fool around. Today, you and I are supported by the taxpayer or a business in some way. We owe something back. All right? I think each one of us should really have that feeling. And from that sense, being useful, I think to me, is very important, and that's something you get. We have a lot of challenges. Okay, one is solving the right problem. I was even telling during conversations with one of the faculty members, anytime you start from a second-hand problem, even given by your customer, the risk that you're solving the wrong problem is very, very high. I told you the story of the signaling guys running around for 2 months, checking cross connects and other things. In the first problem, they came to us saying it's maintenance mucking up. What is the solution? A solution is not a paper, is not a theorem, not an equation. It is something that is implementable in a hardware, okay? So if you're in industry, if you want to be effective, you have to take an end-to-end responsibility. You can't just say, I've done my work, I've given you a paper, go look it up. No. You follow through, make sure it gets implemented, go back, check, is it working the way you predicted it would, and so on. Abstracting the essential, I gave you the story in a very watered way. In each one of these problems, there's so much inessential detail. Throwing that out, honing on what is really the problem, that's where experience and domain knowledge, all that come into play. domain knowledge I already put in. And this is the reality, okay? You have a thesis problem or a project. After a few days or weeks, it's too hard. Okay, I can switch my problem. There's a guide to convince, end of story, right? In the real world, that's not the case. Even if it's not the best, the optimal solution, you still have to give a solution that works. For a simple reason, people, your colleagues have invested a lot of time in you. It's not like I can jump in, know what the problem is, okay? These people have taken time away from their work. Sometimes I've had situations where I had to fly with somebody from New York to LA and back just so that I get time to talk to this person and learn about their system, to solve a certain problem. Because those guys are so busy. This is the only engineer who knows the whole thing, and he's so busy he has no time at work. You want to talk to me, Ram? Are you ready to fly with me? That's the only way, okay? So when they invest that much time in you, you owe them something back. And I already talked about this. If they're skeptical, we need to understand why they're skeptical and not get upset, okay? Unexpected research, unexplored research directions. This is the sad part. There are times when I do feel, if I were in a university, a lot of the things I've listed here as problems which are open, I would have students solving them, would have more work coming out of me, okay? So that's something that you miss. One way I compensate for this is I visit universities. There are many students who have got their thesis problems in places like Brussels, Adelaide, and all based on my visits, discussions. They send me emails, sometimes even call and talk to me. So some problems do get solved, but sometimes what happens is they go in a totally different direction, okay? And damn politics, as I said, okay, that's everywhere, all right? And here's my last slide, and that's my talk. Thank you. Yeah, I can take a few quick questions if you people have the time.
There is time for a couple of questions.
Have you applied this to any of the recent startups like Uber or Airbnb?
No, you see, the work environment that we had was one which would not permit us to apply.
No, but you may not have, but did you hear anybody apply doing theory and others to?
Not that I know of, okay? But right now, that Color IQ that I work with these days, the startup, I do use a lot of algorithmic work. And that is in coming up with a formula for a prescribed color. Exactly.
Any other question? Yes.
One of the takeaways in the first part of the talk was that the system is more efficient if you load it up higher, but then it has the problem of the risk of failing. This we see in transportation systems. You see the financial system.
I have two questions. The first one is, does it give us an excuse to be inefficient? Because we can then claim that we are robust. So that's the first one. The second one is, can we roll in the requirement of efficiency? So we are trying to optimize, we are trying to load the system, but can we also bring in the requirement of mitigating risk as part of our objective? And is there a systematic way of solving and getting to a state where not only we are efficient, we are also mitigating risk to the extent possible? Thank you.
The answer to the first question, okay, I would phrase it this way. If loading the system to a higher level results in an inefficiency that is kind of endemic, okay? There's no way to identify different classes of customers, exercise some control on them, or mitigate it in some way, and also have some reasonable assurance that this is not a control that you will have to invoke 1,000,000 times in an hour. By all means, we should take advantage of the efficiency with controls to take care of those rare circumstances where systems misbehave. As a very simple example, if I'm running a call center, I will not put all my eggs in one basket, the Halfin-Witt theorem. I'll probably put in a control saying, if here is a customer who is really hogging my operator, asking a million questions, maybe after the 4th question, that person should say, look, I'll call you back. Please give me your number. Or have an overflow group which takes care of such troublesome customers, rather than let them into this system which will degrade its performance and capacity terribly. And so it's very, very, very system dependent. But I think this example I talked to you has all the, what shall I say, the essential ideas on it. Okay, it is the details that will depend on specific systems. What was your second question?
Mitigating risk as part of our objective.
I think ideally these should be handled at the design stage, okay? So the answer is yes. Because, it's much harder to fix it. In this case, even putting that Band-Aid took a lot of time and a lot of downtime for customers. The eventual solutions took about 3 years or so to hit the boxes after being licensed to the vendors, and then they put it and they'd go through all the usual testing, okay, all the way through integration, testing, system testing, blah, blah, blah. So it's better to design it and optimize it up front.
So we'll take the rest of the questions offline. So we must thank Dr. Ramaswami for a very interesting talk on all the wonderful things that mathematicians can do in the industry. So may I request Professor Anurag Kumar to present a bouquet, a memento, and also the Institute magazine, which is called Kernel.
Oh.
So thank you very much for coming to this talk. You are now cordially invited for a coffee tea session where you can actually continue to interact with Dr. Ramaswami. Thank you very much.